we can do lots of different 2 degree of freedom systems, but for right now, we're just going to use 2 masses. Oh, that's a spring. And we have a mass 1 and a mass 2, and we have x1 in that direction, and we have x2 in that direction. So first, we have to make an assumption, right? We need to build our free body diagram. We're going to make the assumption that x1 moves more than x2. x2 moves more than x1, so x1 is less than x2. That allows us to say that M2 pulls on M1, right? So you can kind of see how those blocks would pull apart. M2 is going to pull on M1. So if I draw my free body diagram for the left-hand side, I'm going to have a force acting back, because it's moving to the right, of K1, X1. I'm going to have a force acting up and down, but I'm just going to not draw those. And then, of course, we have X1 moving to the right. And now I have a force pulling to the right, because M2 pulls on M1. And that is going to be K2, which is the stiffness of my second string, of X2 minus X1. Does that make sense? So X2 minus X1. And then I have a spring on my left, and on my next mass, and I'm going to have the exact same force, right? Force pulls on one mass, it has to pull on the other mass. They just respond to each other. And now I'm going to have this body here of M2 and M1, and it goes to the right x of 2. I can go ahead and write 2 equations of motions. We all like equations of motions. And so for the first mass, I have M1 x double dot equal to negative K1 x1 plus K2 x2 minus x1. M2 x double dot is equal to negative K2 of x2 minus x1. So I have a little bit of x1 and a little bit of x2 in each equation, right? Yeah.
Is the first one M1 x1 double dot or x2 double dot?
The first one's M1 x1 double dot. Yeah, just like it is. So I've got a little bit of x1, a little bit of x2 in each equation. Right? It's like making a salad. You mix the corn and the lettuce. I'm from Iowa. We put corn in salad. Don't judge me, right?
What's next, or at the top we say make the assumption x1 less than?
That x2 did not write out. That x2 is greater than x1, right? All right, so now I want to rearrange this a bit. I'm going to move 0 to my right-hand side. That's where my forcing functions go. And so we have M1 x double dot of 1 plus K1 plus K2, all in parentheses, times x, whoops, sorry, nope, that's just x1 minus K2x2. K2x2 is equal to 0. And then we have M2 x double dot of 2 minus K2 x1 plus K2 x2 is equal to 0. And I'm going to move that over just a bit to the left so we can get them to arrange a bit more. So though there are two coupled second order differential equations, they each require two initial conditions to solve, right? We need, to solve, we need x10, v10, we need x20 and v20, right? So my displacement for my first mass at time 0, my velocity for my first mass at time 0. That should, hopefully you see that pattern now. So as before, the initial conditions are kind of the constants of integration that we can use to solve. We can write these out. They get quite difficult. However, we will do all of this now in matrix notation. We like matrix notation. It's a much easier way to kind of represent these problems. And so let's go ahead and build out our matrix notation for this problem. I'm going to have M1, 0, 0, M2, x double dot of 1, x double dot of 2. And now I have my first cool thing of the chapter. I have my mass matrix. Anyone ever heard the term mass matrix, stiffness matrix? Few people? Okay.
Maybe once in like a Marvel movie where they were explaining not real science.
Yeah, not real science. I learned about vectors from Despicable Me.
Yeah, I was
Yeah. It's a pretty great line. You need more of that. Okay. Plus K1 plus K2 minus K2 minus K2 K2, and stiffness is multiplied by displacement x1 x2, and that is our stiffness matrix. Equals 0. So we can write it that way. It's a big matrix. Takes a little bit to write. We can also write it like this. And different people use different notations. Different fields use different notations. But we're going to write it in this class as M X arrow double dot plus K X arrow double dot is equal to 0. The arrow shows us it's a vector. The capital K tells us it is a matrix. A lot of people use bold. It's hard to use bold when I'm writing stuff down. So I just use that. Yes?
Why is the x double dot over k for the stiffness? Why is that x double dot?
No, it's not. There we go. All right, so now we have a mass matrix and we have a stiffness matrix. And then we have x vector, x dot vector, and x double dot vector for our displacement, our velocity, and our acceleration. And so we can also do x0 vector is equal to x1 of 0. We're going to write it like that now, x2 of 0. Just writing it in a different notation so you know they're kind of all the same. And we have x0 vector velocity dot is equal to x1 dot of 0, x1 dot of 0.
The x2 dot of 0?
No, because it's my velocity. These are my boundary conditions.
So it's the same.
Oh, this one down here.
Yeah.
Sorry. Yes, x2 dot of 0. So those are my boundary conditions that I use to solve that method. All right, so recall that we can calculate the values of the constants in an assumed harmonic solution and apply our boundary conditions, right? There's a couple different ways we can do that. We can also assume solution, right? You know, but we're going to assume a solution and it'll work because we've pre-solved it. But if you're asked why do we pick this, right? I mean, it's the same one we picked before, so we're just going to make it work. Let's assume the solution that x vector of t is equal to u e to the j omega t. Everyone like that solution so far? We're going to add the u vector in because we know that we need mode shapes. We need mode shapes to connect our system. We just know that from our prior investigation of 2-degree of freedom systems and kind of talking about the importance of mode shapes. So u vector, that's just u1, u2. Right? My first mode shape, my second mode shape. Everything's kind of the same before. Euler harmonic, j equals the square root of -1, omega is the constant to be determined, things of that nature. So we can write that x vector velocity of t is equal to j omega u vector e j omega t, and we can write that x vector acceleration as a function of t is equal to negative omega squared u vector e j omega t, right? That's just taking the integral and taking the integral again. So now we can put those back into the equation of motion. And if we put those back into the equation of motion, what do we get? And again, I'm putting that back into the equation of motion in vector form. So I'm going to get negative omega squared mu vector e j omega t plus k u vector e j omega t is equal to 0. A little bit of rearranging now, I can get that negative omega squared m plus k multiplied by u vector e j omega t is equal to 0. All right, we got an issue here. If you were a mathematician, we would say, well, that's easy. You just make u to 0, or you make e j omega t to 0, and then you have it answer 0, and it solves. Why can't we do that? Yeah, it's not realistic. Like, it doesn't give us a solution that is useful. It is a solution. It's called a trivial solution, right? It is absolutely true, but it is absolutely useless. It is trivial. Not absolutely useless, but it is pointless. So we are going to, not arbitrarily, but we are going to define that those two cannot equal 0. Does that make sense? Because if we let them equal to 0, class is done. And we learned nothing about mode shapes. We didn't learn nothing of helpfulness. So this forms a homogeneous set of algebraic equations, right? So to be useful, let's write it like this. So let's say let's take out the things that we're looking for, and we have negative omega squared m plus k multiplied by u vector is equal to 0, right? We need that to be equal to 0 to get the previous equation to be equal to 0. But again, we're going to say that u vector is not equal to 0, right? So again, you can't just say, oh, all right, we applied one condition, next trivial solution. This forms a homogeneous set of algebraic equations, and so to be useful, these equations have to have a non-zero solution for the system to exist, right? All right, so for this to be true, the inverse of the coefficient matrix must not exist. So the inverse of negative omega squared m plus k must not exist. To expand, assume that it does exist, and then you can multiply both sides of the equation by the inverse, and then that yields u vector equals to 0, and u vector equals to 0 is something that we don't want, right? That would just be no mode shapes, no vibration, not helpful for the solutions that we're trying to find. So that's another trivial solution. So the next logical step, we're just working our way down, right? We're working our way down in terms of the easiest solution, and every time we hit one that results in something trivial, we just neglect it and move on, right? We add another condition. So now we're going to say that the inverse of negative omega squared m plus k can't exist. So the next logical connection can be drawn between the solution of the equation and the inverse of our coefficient of matrix, right? So we want to apply a singularity condition to it. So for that to exist, we say that the determinant of negative omega squared m plus k is equal to 0. So we want to solve that to be true, because then we don't have an inverse to our matrix, right? So solving this expression results in an algebraic equation with one unknown omega. So remember how to solve the determinant for 2 by 2 matrix? Anyone remember how to solve the determinant for a 2 by 2 matrix? What? Python. It's A, B. Remember, you have a matrix A, B, C, D. It's C, B. Yep, perfect. That's what we were looking for. A little bit of groupthink. All right, now that's clear in our mind. We can solve the determinant, right? We just have to build out this matrix. We know how to do that. So determinant of minus omega squared m1 plus k1 plus k2 minus k2 minus k2 minus omega squared m2 plus k2 is equal to 0. All right. A is going to be, so the first term, when we multiply that out and do a little bit of rearranging, I'll just write it out here. We're going to have m1, m2, because it's this term times that term, omega 4, and there's some other things that get multiplied and rearranged, but that's fine, minus a nice big list of m1 k2 plus m2 k1 plus M2 K2 omega squared plus K1 K2 is equal to 0. This expression, if you don't write much down, write that down, is the characteristic equation. And it comes from the solving for the determinant of our coefficient matrix. And we have to solve for the determinant equal to 0 because we can't have an inverse, we can't have mode shapes equal to 0, we can't have ej omega t equal to 0. The characteristic equation can be solved by our good friend, quadratics. Remember quadratic formulas? Yes? No?
Is this the determinant? Is the characteristic equation? Or is this just the AD part of it?
This is the characteristic equation because it has an equal sign. So this is an equation. This is our characteristic equation. And we found it by taking the determinant of the left-hand side still equal to 0. Okay. In theory, you could say that this is another form. You don't write, this is, if you write this down and label it the characteristic equation, nobody will agree with you.
I was confused if it had this, like, I was confused if the characteristic equation had to include the full determinant and not just the AD part.
This is the full.
But what about the plus K2 squared?
Plus.
Or it's just one minus.
It's all rearranged into this.
It's in there.
It's, yeah. It's in there. We can chat afterwards too, if you need, or we can take another look at the notes. But
okay,
yeah.
The CB part of it is minus AD minus CB.
It's all in there.
It's in there. Okay,
it's in there. Sure. Yeah. I just wrote the answer. I don't even in the notes, I don't work through it completely because it's just kind of like, it's there. But let me know if I have a mistake. Absolutely. All right, our good friend, the characteristic equation is in the form of a quadratic formula. So just as a review here, you remember this fun entity plus bx plus c is equal to 0. Remember that one from pre-calc or something like that? So after finding, so we have omega squared, right? So we can set x equal to omega squared. So we have omega to the 4, so we set x equal to omega squared, and then that's how you get to omega to the 4. So now we get a solution for omega 1 and omega 2, where the vector u that satisfies the equation, right? So again, we have two solutions. We have just, again, kind of given you the solutions using the quadratic equation. Negative omega 1 squared m plus k u vector 1 is equal to 0. And now u vector 1 is our first mode shape. Now we have quadratic. I just put an empty. Quadratics give us two expressions, right? So the other one is going to be negative omega 2 squared m plus k u2 vector is equal to 0. So the direction of our u1 and u2 are kind of obtained by solving the expression above. However, the information regarding the magnitude is not contained in this expression, right? The mode shapes are just shapes. Remember that. There's no information about the magnitude of the shapes. The mode shapes are just shapes. So another way to think about that is as u1 vector solves the expression, on a linear system, we can just scale it. You know, let's go alpha u1 vector also solves it. System, you change the amplitude, but you don't change the shape. Mode shapes are mode shapes. All right. So let's say we want values for u1 and u2, right? We want to know our mode shapes for our system. That's pretty basic. Let's take our mode shapes and put them back into our assumed expression, right? So, all right, you tell me that we can do x vector of t is equal to u vector of e j omega t. So we said before that's an assumed solution. We know that solution is going to work out. So let's figure out what that actually means if we're solving for our mode shapes. That forms a set of solutions that are x of t is equal to u vector 1 e j omega 1t, because my first mode oscillates at, my first mode shape is related to the frequency of the first mode. That's why we have an omega 1 and a u1. We also have a oh wait, I messed up. I've got a negative there. I'm going to do it that way. U vector 1 e positive j omega 1t, because I have a positive and a negative solution. And then I have a u vector 2 e to the negative j omega 2t. And I have a u2 e to the j omega 2t. So since the equation to be solved is linear, the solution is the sum of equations, right? So I can add these all up and get a sum of solutions for my solution. I can also throw in arbitrary scaling factors that I have to solve for later, but I'm going to need those because it's a sum of solutions. So because it's linear, again, our only saving grace in this class is everything is linear. We have ae to the j omega 1t plus b e to the negative j omega 1t, all of that multiplied by u vector of 1 plus parentheses c, sorry, those look kind of the same, e to the j omega 2t plus de to the negative j omega 2t u of t. Sorry, not u of t, u2 vector. That's my second node shape, right? Where a, b, c, and d are arbitrary constants of integrations to be determined by the initial conditions. We need this. If you look at this, we have our positive and our negative exponents. And remember the Swiss mathematician turned Russian court mathematician Euler, right? Told us how we can solve for expressions like this back into sines, right? Remember Euler's expression? So using Euler's formula for the sine function, again, assuming, so using Euler, assuming well, let's just say not assuming, where omega 1 or omega 2 is not equal to 0, because if that mass is not moving, right, we have an issue. This expression can become x of t is equal to capital A1 sine of omega 1 t plus phi 1 u1 vector plus a2 sine of omega 2 t plus phi 2 u2 vector. And that is an expression as long as omega 1 or omega 2 is not equal to 0. We can write that in matrix form, but I'll let you do that or take a look. This is 5.36 in the text. I'm going to draw a red box around that one. It's pretty important. So again, A1 and A2 can be obtained by setting and applying the boundary conditions and taking the derivatives of the equations, as we did in a 1 degree of freedom problem. All right. So we found the solution by assuming a solution, solving through until we hit the characteristic, solving through until we hit our coefficients here. And then we said ej omega t can equal to 0. So I take it down to my next solution and I say, well, u can equal to 0 because that would be trivial. So I take it to my next solution. Well, then negative omega squared m plus k can't have an inverse because I just multiply it by the inverse and I get 0. So that's another trivial solution that I want to knock out. And then I know that I have to have an inverse. So if I have to have an inverse, then my determinant has to be equal to 0. I write that out. I get my characteristic equation. From my characteristic equation, I'm now at my omega 4 terms, right? I can solve my characteristic equation using a quadratic formula, right? So then I have two solutions, positive and negative. And then once I get back in the solutions positive and negative, I get something that looks like an Euler's expression, and I can use Euler's to get back into a real solution.